All right. This is just a simple, right? Simple two unknown, two equation type algebra. Or is it? No, it isn't. This is actually a really tough problem to solve, which requires you using tricks in order to solve it. You know, what types of tricks? Well, the tricks we've been, talking about anyway. So this is something that's not so easy to solve without having to do something, right, to figure it out. Anyway, but this is not required because of this. If we run into a situation where we have to do simultaneous, then you could stop and just say, well, this has to be solved simultaneously. If you say that and you recognize that it has to be solved simultaneously, then you get full credit for the problem. You don't actually have to solve it because there's a lot of algebra involved. It's not just pure algebra, but it's algebra and chemistry because you have to make some assumptions, simplifying assumptions in this, I think, to recall, in order to come up with an answer. But anyway, I mean, you could, it's not, I've solved it myself, using some little tricks here and there. And students have done it too, so if you're gung-ho and you want to solve it, go ahead and solve that. It might take you a while, right, to solve the algebra because it's not easy. So you could just leave it there, but if you do solve it or if you do set it up like this, then you can get some extra credit. Now the book actually covers this problem. They don't solve it either, because it's hard. Well, they give you some hints though. The book will give you some hints. So let's take a look at what the book says about this. One thing the book always does is they don't write out the ice tables completely. What they like to do is they just like to compress it into one line. I like to keep it separate because I like to solve all the problems in the same way, and the book and the solutions manual is always going to do this. They compress it to here. We use the different variables though. The variables they use are these here. But you can see how we set it up. We set it up a little bit differently than how they did it. Essentially, it's the same thing. All right. So this is for a very dilute solution of a weak acid, 16.2. They get two equations and two. Actually, they have three unknowns here, but we need to know what M is, the molarity. This is usually given. And so if we know what M, the molarity is, then we have an equation that looks like these here, right? And then they give you some hints here. What are the hints they give you? Okay, when we solve the K expression for X, we obtain this. Actually, they kind of walk you through it. And when we substitute these values of X and X plus Y into the KW equation, we get this. So our variables are different because we chose different letters, I think. The value of Y satisfying this equation is not difficult to obtain by the method of successive approximations illustrated in Appendix A. The solution of this problem is left for you to do. See exercise 89. Except if you go to exercise 89, the solution manual screwed it up. If you look at the solution, the answer for problem 89, the book's solutions manual is totally wrong. You'll see it. It's obviously wrong. Unfortunately, I don't know why they didn't fix it. But you'll find that for this, the pH, this certainly seems reasonable. Finally, we can use the results of the previous discussion to establish a criterion. So here we do this by making assumptions. These assumptions simplify the math and try to make your life easier. And so these are some additional tricks you have to use for solving this. So you can read through that if you're interested in doing that. All right, we're going to move on now. We have to just be aware. Do we want to solve every problem the proper method? Every problem, multiple equilibria, should be solved using the simultaneous method, but you can see the math is just way too horrendous. If we had to solve every problem like this, it'd just take hours just to solve one problem. And so this is why we try to use the stepwise method and hope that it doesn't perturb, because if it doesn't perturb, then we're safe. You know, we don't have this endless loop problem. Fortunately, most of the problems are going to be okay with the stepwise method. Just occasionally we'll run into a problem in which it fails, and we have to recognize when it fails. When you go, take a look at the solutions manual to exercise 89, and you can see that they didn't even check to see if the one step perturbs the other. It's like they had two different hydroniums in the beaker, and it's in the same beaker. You can't have that. Two different hydronium concentrations in the same container of water and other. All right, so let's take a look at another example here. And all problems, just going to try out stepwise, H2SO4. You know, so when we get to very low concentrations, like, you know, these low concentrations here, you have to start worrying. Now, after we do a bunch of these, we start worrying. Like, for example, well, I'll talk about it after this one. We'll talk about it. So in this one, this is what we call a polyprotic acid. Polyprotic acids are going to be like H2A. That would be a diprotic. Or H3A, which would be a triprotic. So we'll have diprotic and triprotic acids. Well, this is where A is just equal to some generic anion, whatever anion the acid has. So if we have a diprotic acid like H2A, you know, there's going to be a Ka equation that we can generate. This is going to form H3O plus HA minus. We just lose one proton at a time. We don't lose both protons. They don't break off simultaneously. So a base comes, water, and attacks one proton, pulls it off, and forms hydronium. This we call Ka for H2A, but it's also known as Ka2 for H2A. And it's just going to be, you know, the hydronium times the HA minus over the H2A concentration. But this is diprotic acid, and diprotic acids have two acidic hydrogens. The second acidic hydrogen is on HA minus, and so HA minus can also collide with water once it's generated. So we generate some HA minus, the HA minus collides with water, and that in turn can form additional hydronium and A2 minus. And so this would be the Ka for the acid anion, which we call HA minus. And so anions can also have Ka values as long as they can collide, generate hydronium. But this is also known as Ka2, you know, the second ionization for H2A. So it would be, oops, this is wrong. This is Ka1, this is Ka2. And Ka2 for H2A, or Ka for HA minus, is just the hydronium times the A2 minus divided by the HA minus concentration. This is all generic. Triprotic, the only thing about triprotic is there'd be one more step. So triprotic is going to have, you know, diprotic acid will have Ka1, Ka2. A triprotic acid will have Ka1, Ka2, and Ka3. 3 acid hydrolysis steps for each successive hydrogen on there. Okay, well, I'm sorry?
Sorry, we're still writing. Yeah.
Oh, you're still writing that?
Yeah,
Oh, all right. Wow. Well, you're going to see it right here. We're going to write it out. For H2SO4 then, this is, if I have a beaker that's 0.100 molar H2SO4, you know, there's only one hydronium ion concentration in there. You know, but it turns out there are going to be 3 hydronium ion producing reactions. Ka1, Ka2, and Kw. You know, all these equilibria are tied together because all of them produce hydronium. And so we will we'll take care of each of these ones here. And that is, in step 1, we have H2SO4 plus H2O liquid. This is going to give us hydronium plus HSO4 minus. Ka for this is, you should have the Ka value for this memorized. What is a Ka value? It's a strong acid. Yeah, Ka for this is very large. You know, Ka being very large, it just says that the hydronium ion concentration times the HSO4 minus concentration over the H2SO4, you know. Well, what should the H2SO4 concentration be? It's a strong acid. Strong acids ionize completely. So H2SO4 concentration should go to 0. You know, all these. So if we start off initial, 0.100 molar, it's a strong acid, so we should lose all of it, just like the HCl. The HCl is a strong acid, we should lose all of it. So we know what X is, or Y, or whatever. We're going to lose how much? We're going to lose 0.100. It's a complete reaction. And so therefore, we're left with 0 molar. Well, Ka has got to be very large because at equilibrium, if we have 0 in the denominator, then Ka better be infinity. But it's not really infinity, it's far short of infinity. So this is why we use this very large, because this is how we're going to deal with this. Water is a liquid, so X that out. Hydronium is 0 and 0 to start. None, it's going to be 0.100 molar here, 0.100. And so it's completely hydrolyzed, aka it's completely ionized. All right, this is step 1. Okay, now what is step 2? Well, it depends. What's bigger, Ka2 or Kw? Well, Ka2, we looked that up in the book, or that chart over there. Ka2 is 0.011, Kw is 1.0 times 10 to the minus 14. So we go in order. We start off with the biggest K and then work our way down. And so we have to look. It's not always Ka2 that's next. Sometimes it's Kw, depending on how weak Ka2 is. And so this was step 1. Sorry. What we're going to do for step 2 is we're going to do Ka2. And so we're going to take HSO4 minus that was generated here, HSO4 minus, and let that hydrolyze with water, H2O liquid. This is going to form hydronium plus SO4 2 minus. This is what we call Ka2. For H2SO4. Ka2 for H2SO4 is going to be the hydronium ion concentration times the sulfate ion concentration at equilibrium divided by the HSO4 minus concentration. Is HSO4 minus a strong acid? Can we say, okay, this is going to go 100%? No, it's a weak acid. Weak acid is only partially ionized, partially hydrolyzed, and its K value is only 0.011. It's not infinite or very large, right? And so we have to figure out, but how much HSO4 minus do I have initially? Yeah, I'm going to have 0.100, and so this HSO4 minus here is what I used to start step 2 with, because I generated the HSO4 minus in step 1. I'm going to use it in step 2. It's going to collide with water. Water is pure liquid, so let's blank those out. How much hydronium do I have to begin with? Well, I'm going to assume none of the HSO4 minus has reacted yet, right? Mm-hmm. And so should I have 0 here for the hydronium? This is very tricky because I'd like to put 0, and I get in the habit of putting 0, but it's not really 0. Because I generated hydronium in step 1. So I actually have 0.100 molar here to start, but I have 0 molar sulfate because I'm assuming that the HSO4 minus hasn't collided with anything yet. So which direction is the change going to be here? To the right or to the left?
To the right.
To the right, so it's going to be minus X molar plus X molar. Be careful. In chapter 16, it's always a 1-to-1-to-1 ratio. But in chapter 15, you have a 1-to-2 or 2-to-3 or whatever ratio. And so a lot of people forget, like if there's a 2 here, they forget to write 2X. Because of chapter 16 coming right after 15. And so this is going to be 0.100 minus X. And they also forget to write squares. In chapter 16, you see there are no square terms here, cube terms. You know, the worst is going to get is quadratic. But in chapter 15, it's much more variety. And so X molar. Well, that makes sense because we're just focusing on acids right now, and bases. All right, so let's go ahead and plug this in and solve for X. So we're going to get 0.100 plus X times X divided by 0.100 minus X. And then I just automatically try the simplifying assumption. We just try the simplifying assumption that's going to come out to 0.100 times X over 0.100. And this is easy because then X is just equal to 0.011. Well, if this is 100, then that's 11. So it turns out this is 11% change. Unfortunately, 11% change is too big. So we can't use a simplifying assumption here. We have to use a quadratic. So let's go ahead and solve the quadratic.
So when you do the simplifying assumption, I noticed that sometimes you take away both of the x's, sometimes in the parentheses, and sometimes you only take out one, and other examples. And why is that?
Well, I never take out this x outside the parentheses.
Yeah, only on the inside.
But yeah, okay. I only did it once where I might have taken away an x in one but not the other. It depends on the initial amount. If one initial is like a swimming pool, then I'll take it away. If the other initial is like a thimble of water, I wouldn't take it away. So it would be a selective. It would be, that was what I called advanced technique for the simplifying assumption. Otherwise, I take it away from both. I always take it away from both, or however many there are. I take it away from all of them. Okay. Anyway, we need to get that into quadratic form. So let's do that shot. So 0.100, 0.1 times 0.011 is 0.0011 minus 0.011x is equal to x squared plus 0.100x. All right, let's add this 0.011x to both sides and subtract this. So I'm going to get x squared plus 0.111x minus 0.0011 is equal to 0. Okay, can somebody solve this for x? Uh-huh. 0.00915. Okay, thanks. Is that what other people got? No, you got something different?
I got
Yeah.
0.0631.
0.0631? 0.0631. You got this? Okay. All right, so let's go ahead and calculate the concentrations. This is going to be 0.100 minus 0.00915. You're going to give me 0.09085 molar. And then over here, I'm going to add that. So this is going to equal 0.10915. And this is gonna be 9 point, actually, we'll just do it here, 0.00915. But we should check the K first. Let's check our K value and make sure these concentrations work.
I got 0.0109.
0.0109, which would round to, if this was 2 sig figs, it would round to 0.011, so it checks out. This is good. But when we do it stepwise, we have to make sure that step 2 does not perturb step 1. Because we increased it about 10%, right, the hydronium. Did step 2, well, it's going to perturb it. Because if we increase this concentration by 10%, Le Chatelet's principle says shift left and we end up in the endless loop. But in this case, we don't because step 1 is special. Step 1 is a strong acid. Strong acid is only a one-way reaction. One-way reactions like this are not affected by Le Chatelet's principle. And so it should perturb it, but it doesn't because step 1 is a strong acid. So we're safe so far, but we have one more step, step 3. And so we don't know if stepwise will work yet completely because of step 3. So did everybody get that? There's no Le Chatelet's perturbation of step 1 because, somebody tell me,
You think step 1 is strong acid?
strong acid.
Yeah, it only happens
Yeah, it only happens one. All right, so let's go on to step 3. For step 3, there's one more equilibrium, and this is also going to impact the hydronium ion concentration here. So we have hydronium and hydroxide. Water, we ignore that liquid. Okay, the initial hydronium is, we aren't done yet, you know. This is no longer the hydronium ion concentration in the beaker, is it? No, because we added some, we added X to it. Well, this is no longer going to be the hydronium because we're going to add some more hydronium to it in step 3. And so from step 2, we get 0.10915 molar. And then we're going to assume no hydroxide has formed yet. That is, no water molecules have been allowed to collide. And then we're going to get plus X molar here, plus X molar here. And so at equilibrium, I'm going to have 0.10915 plus X molar, and then X molar. All right, and what I want to do here is, let me erase part of this. We'll plug this in. Kw is equal to the hydronium times the hydroxide. And that's going to equal 0.10915 plus X times X. I'm just going to use a simplifying assumption here. This has got to equal 1.0 times 10 to the negative 14. You have to memorize that. So this is going to be 0.10915 times X. And therefore, X is what?
(9.161) e to the negative 14.
9.161
161 e to the negative 14.
times 10 to the negative
Yeah. Negative 14.
14.
Yeah.
All right, let's calculate the percent change. Percent change, I'm just going to do order of magnitude because the initial is 10 to the minus 1. The change is 10 to the minus 14. So 10 to the minus 14 over 10 to the minus 1 times 10 squared percent is going to give us 10 to the that? 10 to the minus 13, 10 to the minus 11, wow. And so this is gonna be about a 10 to the minus 11% change, roughly. This is all just rough calculations, which is totally fine. If you see a percent change this small, then if you do the quadratic, you're gonna get the same answer, basically. Not even worth doing the quadratic. And so what this means is this: we're gonna have 0.10915 plus, we're gonna get some more hydronium in this step. Well, how much more hydronium? Is this what other people got for the X? Just wanna make sure before I move on. Yeah? Okay. Well, how much hydronium? Well, this is 10 to the minus 14, so I need 13 zeros. So I'm gonna go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, and then a 9, 1, 6, 1. And that means I'm going to need 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 8. So I got 0.10915, and then let's go with 8 zeros. 1, 2, 3, 4, 5, 6, 7, 8, 9, 1, 6, 1. All these are insignificant anyway. Molar. And so that's that, and then the hydroxide is going to be 9.161 times 10 to the minus 14. And let's check to make sure it works out. So can somebody calculate it? Let's see. Yes, it works out. Okay, K checks out. Now, we have to worry about Le Chalet's principle. That is, step 3 increased the hydronium. Yes, it did because we added a little bit of hydronium. Will this perturb step 2? So how much additional hydronium did we add? We added this much additional hydronium in step 3. Is that going to really change things much? No, this is what we call a negligible. It doesn't even register. You can't even punch that into your calculator. This is negligible increase. If it's negligible increase, then we say it will not perturb the previous step. And so we lucked out two times. Step 2 was a significant increase over step 1, but we were lucky because step 1 was a strong acid. And then step 3, it was a negligible increase, and therefore we lucked out again. We don't have to worry about it in perturbing step 2. And so altogether, this is what we're going to have in this beaker. What we're going to have in this beaker, this is labeled 0.100 molar H2SO4. And so the H2SO4 concentration is 0 molar. That is, we don't have any molecules of H2SO4. Instead, we have ions. Like the hydronium ion is going to be this one, 0.10915 ... molar. I'm not going to write all the digits. And so this is the hydronium ion concentration here. We're also going to have hydroxide in here. Hydroxide is going to be 9.161 times 10 to the minus 14 molar, very little hydroxide. And then we're going to have HSO4 minus here, 0.9085 molar. And then we're going to have sulfate over here. Sulfate is going to be 0.00915 molar. And then from step 1, the hydronium and HSO4 minus, which travel down there. And so this would be the solution inventory here. When we do this, this is called the solution inventory. These are the species we find in solution and their concentrations. So this is what we call the solution inventory. If we were only interested in the pH, though, would we have to do all 3 steps? Well, for the solution inventory, we have to do all 3 steps. But if we were interested in the pH, did that final step, step 3, really change the pH? No. And so we're going to take a shortcut. We're going to take the Chem 4 shortcut for a lot of these calculations and skip the final steps, because usually those final steps don't. And so we need some kind of criteria. You know, when are the final steps important, when are they not important? So we'll talk about that later. I'll stop here.